Welcome to Sleepless Astronomer, where we explore the wonders of space and the universe. If you're enjoying these cosmic journeys, please like this video and subscribe to the channel. We post new videos every single day, so you can tune in whenever you want to learn about the cosmos. And we'd love to hear from you in the comments. Let us know where in the world you're watching from. We always enjoy connecting with fellow space enthusiasts around the globe. Now let's begin tonight's journey through the universe. How life could survive on rogue planets. Most planets orbit stars, bathed in starlight that provides warmth and energy for any life that might evolve. But scattered throughout the galaxy are worlds that wander alone through the darkness of interstellar space. Rogue planets, ejected from their birth solar systems through gravitational interactions, or perhaps forming in isolation, drifting for billions of years without a sun to orbit. These orphaned worlds seem like the least hospitable places imaginable for life. Cut off from starlight, they receive no external heat source, no energy for photosynthesis, no warming to maintain liquid water on their surfaces. Yet despite these apparently insurmountable obstacles, life might still find ways to survive on rogue planets, drawing on internal heat sources, subsurface environments, and the remarkable adaptability that evolution has demonstrated countless times on Earth when organisms colonize seemingly impossible habitats. The key to habitability on rogue planets is internal heat. Unlike stars, which generate heat through nuclear fusion, rogue planets must rely on residual heat from formation and ongoing heat from radioactive decay of elements in their interiors. When planets form, the process of accretion, countless collisions between smaller bodies that gradually build up the planet, converts kinetic energy into heat. Additionally, gravitational compression, as material piles up, releases energy that heats the planet's interior. A newly formed planet is molten or partially molten, taking millions to billions of years to cool. This primordial heat, combined with heat from radioactive decay of uranium, thorium, potassium, and other radioactive isotopes in the planet's rocks, keeps planetary interiors warm for billions of years. Earth itself generates about 47 terawatts of internal heat, roughly equal to 10,000 large power plants operating continuously. Most of this heat comes from radioactive decay, with some contribution from residual primordial heat and from crystallization of Earth's molten iron core. This internal heat drives plate tectonics, powers volcanic activity, and maintains Earth's magnetic field. A rogue planet of similar size and composition would generate similar amounts of internal heat, regardless of whether it orbits a star or drifts through interstellar space. The challenge is keeping that heat trapped. Without an atmosphere, heat would radiate directly into space, and the planet's surface would quickly reach temperatures only a few degrees above absolute zero, the background temperature of the universe, about minus 270 degrees Celsius. But a substantial atmosphere could act as insulation, trapping heat through the greenhouse effect and maintaining warmer temperatures at the surface or in the lower atmosphere, even without any external heat source. A rogue planet with a thick hydrogen atmosphere could potentially maintain surface temperatures warm enough for liquid water through atmospheric pressure and greenhouse warming alone. Hydrogen is the lightest and most abundant element in the universe, and large planets can capture and retain massive hydrogen envelopes during formation. The greenhouse effect from a thick hydrogen atmosphere, combined with internal heat radiating from below, could create a temperature profile that allows liquid water to exist at the surface or at some depth within the atmosphere, where pressure and temperature are both suitable. Computer models suggest that a rogue planet several times Earth's mass, with a hydrogen atmosphere perhaps 100 times more massive than Earth's atmosphere, could maintain surface temperatures above the freezing point of water for billions of years, powered only by internal heat. Such a planet would be entirely dark at the surface, no day or night, just eternal darkness. But it would be warm enough for liquid water, and where there's liquid water and a source of energy, life becomes possible. Life on such a world could not depend on photosynthesis, but that's not necessarily a problem. On Earth, entire ecosystems exist in permanent darkness, sustained by chemosynthetic bacteria that extract energy from chemical reactions rather than sunlight. Deep-sea hydrothermal vents host thriving communities where bacteria oxidize hydrogen, sulfide, methane, or hydrogen, using the chemical energy to build organic molecules from carbon dioxide. These chemosynthetic bacteria form the base of food chains that support tube worms, clams, fish, and crustaceans, all living in absolute darkness, kilometers beneath the ocean surface. A rogue planet with liquid water oceans, maintained by internal heat and atmospheric greenhouse warming, could develop similar chemosynthetic ecosystems. Volcanic activity would vent gases like hydrogen, hydrogen sulfide, methane, and carbon dioxide into the water and atmosphere. Bacteria could evolve to extract energy from these chemicals, building organic molecules that could support more complex organisms. The entire biosphere would operate on chemical energy from the planet's interior rather than solar energy, making the planet's life forms independent of any star. Subsurface oceans represent an even more plausible habitat for life on rogue planets. Many worlds in our solar system likely have liquid water oceans beneath ice shells. Europa, Enceladus, possibly Titan, Ganymede, Callisto, Pluto, and other bodies. These oceans are kept liquid by tidal heating from their parent planets, or by internal radioactive heating. A rogue planet with sufficient internal heat and a thick ice shell could maintain a subsurface ocean indefinitely, with the ice providing insulation that prevents the ocean from freezing while protecting it from the harsh radiation and extreme cold of interstellar space. The ice shell on a rogue planet might be very thick, perhaps tens or hundreds of kilometers, creating an insulating layer that traps internal heat far more effectively than any atmosphere. The ocean beneath this ice would be completely dark, protected from the radiation that fills interstellar space, and stable for billions of years. Temperature would be maintained by heat flowing from the rocky mantle below. Hydrothermal vents on the ocean floor would provide chemicals and energy for chemosynthetic life. Such an ocean might be an ideal habitat, more stable than surface oceans on planets orbiting stars where stellar evolution, asteroid impacts, and climate variations create periodic catastrophes. Life in a subsurface ocean on a rogue planet would never know stars exist. The entire biosphere would be confined to the dark ocean, with the ice ceiling above and rocky floor below defining the limits of the habitable universe. Evolution would never produce eyes sensitive to visible light, because no visible light exists. Organisms might instead evolve chemical sensing, pressure sensing, electroreception, or other non-visual senses. Intelligence, if it evolved, would develop without ever seeing stars, planets, or anything beyond the ocean's boundaries. Such a civilization might not even realize that a larger universe exists beyond their world, having no way to detect or observe the space around them through kilometers of ice. Geothermal pockets could create localized habitable zones even on rogue planets without global oceans. Volcanic activity or concentrations of radioactive elements could heat specific regions, melting ice to create underground lakes or pockets of liquid water embedded in ice. These isolated water bodies might be small, perhaps only a few kilometers across, but they could persist for millions of years, long enough for life to evolve and diversify within each pocket. Different pockets might develop different ecosystems in isolation from each other, creating multiple independent evolutionary experiments on a single rogue world. Atmosphere composition would profoundly affect habitability. A rogue planet that retained or captured a hydrogen-helium atmosphere during formation could use that atmosphere's greenhouse effect to maintain warmth. Carbon dioxide, methane, and ammonia are all more effective greenhouse gases than hydrogen and would enhance warming at much lower atmospheric masses. A rogue planet with a thick carbon dioxide atmosphere and substantial internal heat might maintain temperatures warm enough for liquid water with a much thinner atmosphere than a hydrogen-dominated world would need. The size of the rogue planet matters significantly. Larger planets generate more internal heat from radioactive decay simply because they contain more radioactive material. Larger planets can also hold thicker atmospheres through stronger gravity and lose heat more slowly because their surface area to volume ratio is smaller. Heat escapes through the surface, but heat is generated throughout the volume, so larger planets stay warm longer. A rogue super-Earth several times, Earth's mass might remain habitable for far longer than an Earth-mass rogue planet, potentially maintaining surface or subsurface liquid water for tens of billions of years or more. Very small rogue planets, Mars-sized or smaller, would struggle to maintain habitability. They would cool quickly, losing internal heat within a few billion years. Their weak gravity would allow atmospheric escape, making it difficult to maintain the thick atmospheres needed for greenhouse warming. However, even small rogue worlds might maintain subsurface liquid water in deep aquifers or isolated pockets warmed by concentrations of radioactive elements or by residual heat from formation for some period after being ejected from their parent system. The abundance of rogue planets remains uncertain, but some estimates suggest they might outnumber stars. If planets are commonly ejected during the chaotic early phases of planetary system formation, the galaxy might contain billions or even trillions of rogue planets drifting through interstellar space. Most would be cold, dark, and apparently lifeless at their surfaces, but some fraction might maintain subsurface oceans or possess the right combination of size, composition, and atmosphere to support life in hidden biospheres, beneath ice or in dark surface oceans sustained by nothing more than the planet's internal warmth. Detecting life on rogue planets would be extraordinarily challenging. These worlds emit no reflected starlight, making them nearly impossible to detect through traditional astronomical methods. They can only be detected through gravitational microlensing. When a rogue planet passes in front of a distant star from Earth's perspective, its gravity briefly magnifies the star's light, or through direct detection of their infrared emission, the faint heat radiating from their surfaces. Neither method provides information about atmospheres, surface conditions, or potential habitability, let alone biosignatures. Future infrared telescopes might be able to detect the warmest rogue planets and potentially characterize their atmospheres if those atmospheres are thick enough to produce detectable spectral features. Finding methane, carbon dioxide, or other gases in unexpected ratios might hint at biological activity, though distinguishing biological from geological sources would be nearly impossible without additional information. Direct exploration by spacecraft seems impractical, given the vast distances between stars and the difficulty of even locating rogue planets, let alone traveling to them. The evolutionary trajectory of life on rogue planets might differ fundamentally from life on planets orbiting stars. Without the regular day-night cycle that drives circadian rhythms on Earth, organisms would have no reason to evolve timekeeping mechanisms tied to planetary rotation. Without seasons caused by axial tilt and orbital motion, there would be no seasonal cycles, no annual rhythms. Life would exist in an eternal, unchanging environment, at least on timescales shorter than geological epochs, potentially leading to very different evolutionary pressures than life on Earth experiences. The isolation of rogue planets creates another interesting possibility. These worlds might serve as interstellar arcs, carrying life between star systems. If a planet with a biosphere is ejected from its home system, life on that planet doesn't necessarily die. If the planet maintains subsurface oceans, through internal heating, life in those oceans could survive indefinitely, potentially for billions of years, as the planet drifts through the galaxy. Eventually, such a planet might be captured by another star system, or it might pass close to a star that warms the planet temporarily, allowing surface life to revive if it was dormant. This mechanism, planets carrying life between star systems, represents a form of panspermia that could spread life throughout the galaxy. How life could survive on rogue planets demonstrates the resilience and adaptability of biology when provided with even minimal requirements. Liquid water, chemical energy, raw materials, and time. A rogue planet cut off from all starlight, drifting through the darkness of interstellar space for billions of years, seems like an impossible place for life. Yet internal heat and thick atmospheres, or ice shells, could create hidden habitats where chemosynthetic ecosystems thrive in eternal darkness, where evolution operates unconstrained by day-night or seasonal cycles, where intelligent beings might arise never knowing that stars exist, and where life demonstrates its ultimate independence from sunlight, proving that biology requires not a sun to orbit, but merely the right chemical conditions and energy sources, expanding the definition of habitable environments to include not just planets in stellar habitable zones, but potentially countless dark worlds adrift in the spaces between the stars, each one a potential harbour for life in the vast ocean of the galaxy. The extreme environments where life could thrive. Life on Earth exists in places that seem utterly hostile to survival, in boiling hot springs where water approaches its boiling point, in frozen Antarctic lakes where temperatures remain below zero year-round, in crushing depths of the ocean where pressure would flatten most organisms instantly, in intensely acidic pools that would dissolve metal, and in radioactive waste sites where radiation levels would kill a human in hours. These extreme environments, once thought to be sterile and lifeless, actually teem with organisms called extremophiles, life forms that not only survive but thrive in conditions that would destroy most familiar creatures. Understanding where these extremophiles live and how they manage to exist in such harsh conditions reveals that life's possibilities extend far beyond the comfortable, temperate zones we associate with habitability, suggesting that alien life might flourish in environments throughout the universe that we would never have considered searching. Temperature extremes represent one of the most dramatic challenges for life. At Yellowstone National Park and similar geothermal areas worldwide, hot springs reach temperatures near or even above the boiling point of water. In these scalding pools, organisms called thermophiles and hyperthermophiles thrive at temperatures that would cook most life forms. Some bacteria live comfortably at temperatures around 180 degrees Fahrenheit, and certain archaea, single-celled organisms distinct from bacteria, can survive and reproduce at temperatures exceeding 230 degrees Fahrenheit in superheated water under pressure that prevents it from boiling. These heat-loving organisms have specialized proteins that maintain their structure at high temperatures instead of denaturing and unfolding like normal proteins would. Their cell membranes contain special lipids that remain fluid and functional at temperatures where ordinary membranes would fall apart. Their DNA includes protective mechanisms that prevent the double helix from separating under thermal stress. Every aspect of their biochemistry has been optimized through evolution to function at temperatures that would destroy conventional life in seconds. The existence of thermophiles suggests that life could exist in hot environments throughout the solar system and beyond, in volcanic hot springs on Mars, in heated cracks near lava flows on Jupiter's moon Io, or in the scalding oceans of planets closer to their stars than Earth is to the Sun. At the opposite extreme, psychrophiles, cold-loving organisms, thrive at temperatures well below the freezing point of pure water. In Antarctica, microbes live in lakes that remain liquid beneath ice, because salt lowers the freezing point, maintaining temperatures around -5 to -20 degrees Fahrenheit. These organisms produce antifreeze proteins that prevent ice crystals from forming inside their cells, manufacture enzymes that remain flexible and functional at temperatures where normal enzymes become rigid and useless, and slow their metabolisms to conserve energy in the cold. Some bacteria found in permafrost remain viable after being frozen for hundreds of thousands of years, suggesting remarkable cold tolerance. The discovery of psychrophiles revolutionized thinking about where life could exist in the solar system. Europa, Jupiter's ice-covered moon, has a liquid ocean beneath miles of surface ice, kept liquid by tidal heating from Jupiter's gravity. The water at the bottom of this ocean, near Europa's rocky core, might be relatively warm, perhaps just above freezing, and could host psychrophilic life adapted to darkness and cold. Enceladus, Saturn's small moon, shoots geysers of liquid water through cracks in its ice shell, water that comes from a subsurface ocean. Despite the frigid surface temperature of -330 degrees Fahrenheit, the ocean beneath remains liquid, warmed by tidal forces. Life in these hidden oceans would need to tolerate extreme cold, total darkness, and high pressure, but Earth's psychrophiles prove that temperature alone doesn't preclude life. Pressure creates another extreme that life has conquered remarkably. In the Mariana Trench, the deepest part of Earth's oceans, pressure reaches about 16,000 pounds per square inch, more than 1,000 times atmospheric pressure at sea level. This crushing pressure would compress gases, alter protein structures, and collapse air-filled spaces in ordinary organisms. Yet the trench is inhabited by fish, amphipods, bacteria, and other creatures specifically adapted to extreme pressure. These organisms have no air-filled swim bladders that would collapse. Their proteins are stabilized by special amino acid sequences and by molecules called piezolites that counteract pressure's effects on molecular structure. Their cell membranes contain unsaturated fatty acids that remain fluid under pressure instead of becoming rigid. The existence of barophils, pressure-loving organisms, suggests that life could exist in the high-pressure environments found deep within planets and moons. The subsurface oceans of Europa and Enceladus experience significant pressure from the weight of overlying ice. The deeper regions of these oceans, near the rocky seafloor, would experience pressures far exceeding anything at Earth's surface. Yet if Earth organisms can adapt to pressures in the Mariana Trench, alien organisms might adapt to even higher pressures in alien oceans. Some scientists even speculate about life existing in the liquid metallic hydrogen regions deep within gas giants like Jupiter, though the extreme temperatures and pressures there would require biochemistry completely unlike anything on Earth. Acidity represents another extreme environment where life flourishes. Highly acidic environments with pH levels below 3, comparable to battery acid or stomach acid, would dissolve most biological molecules and disrupt normal cellular processes. Yet acidophiles thrive in such conditions. Iron Mountain in California hosts drainage from abandoned mines with pH levels below 0, more acidic than concentrated sulfuric acid. Despite this extreme acidity, bacteria and archaea live in these toxic streams, deriving energy from oxidizing iron and sulfur. These organisms maintain neutral pH inside their cells while existing in incredibly acidic environments, pumping protons out of their cells faster than the acidic environments can push them in, a process that requires substantial energy but allows survival in places nothing else can tolerate. At the opposite extreme, alkalophiles live in highly alkaline environments, with pH levels above 9 or even above 11. Soda lakes like Mono Lake in California and Lake Magadi in Kenya have pH levels around 10, nearly as caustic as bleach. Microorganisms in these lakes have adapted to maintain their internal chemistry despite the harsh external conditions, using specialized proteins and transport mechanisms to survive. The existence of life in both extremely acidic and extremely alkaline environments suggests that pH is a challenge. life can overcome through evolution, expanding the range of potentially habitable environments to include caustic lakes and springs on other worlds. Salinity creates osmotic stress that would kill most organisms. Normal cells placed in very salty water lose water through osmosis and shrivel up. Yet halophiles, salt-loving organisms, thrive in hypersaline environments like the Dead Sea, where salt concentration exceeds 30%, and in salt evaporation ponds, where salt approaches saturation. Some archaea not only tolerate but require high salt concentrations to survive. They accumulate potassium and other ions inside their cells to balance the external salt concentration, preventing osmotic water loss. Their proteins are specifically adapted to function in high salt conditions and would actually denature and unfold in normal salt concentrations. Hypersaline environments might exist on Mars, where briny water could remain liquid at temperatures below the freezing point of pure water. Salts detected on Mars's surface could create localized regions where salty water exists seasonally or sporadically. If life ever existed on Mars, or if it exists there today, it might persist in these briny environments, sheltered from the planet's coal-thin atmosphere by adaptation similar to Earth's halophiles. Radiation represents one of the most challenging extremes. Ionizing radiation damages DNA, breaks apart molecules, and creates reactive free radicals that wreak havoc on cellular chemistry. Yet radio-resistant organisms can survive radiation doses thousands of times higher than would be lethal to humans. The bacterium Deinococcus radiodurans can withstand radiation exposure of several million rads, enough to shatter its DNA into hundreds of fragments and completely repair its genome within hours, reconstituting functional chromosomes from the pieces. This organism accumulates high concentrations of manganese compounds that protect its cellular machinery from radiation damage and possesses redundant copies of its genome, along with extraordinarily efficient DNA repair mechanisms. The discovery of radio-resistant life expands possibilities for life in high radiation environments throughout the universe. Mars's surface experiences high radiation levels because Mars lacks a strong magnetic field and thick atmosphere to shield the surface from cosmic rays and solar radiation. Any surface life on Mars would need radiation resistance. The moons of Jupiter, particularly Europa, exist within Jupiter's powerful radiation belts and experience intense radiation bombardment. Life in Europa's subsurface ocean would be shielded by miles of ice, but any organism near the surface would need extreme radiation tolerance. Desiccation, extreme dryness, challenges life by removing the water necessary for biochemical reactions. Yet xerophiles can survive in nearly waterless environments. Microorganisms have been found in the driest deserts on Earth, in salt crystals, and even in the upper atmosphere. Some organisms, like tardigrades, microscopic animals also called water bears, can enter a state called cryptobiosis when they dry out. In this state, they replace water in their cells with protective molecules like trehalose sugar, essentially turning into a glass-like solid that can survive for years or decades without water, then rehydrate and resume normal activity when water becomes available again. The ability to survive desiccation suggests that life could persist in extremely dry environments like Mars, where liquid water is rare and exists only transiently. Organisms in a cryptobiotic state could wait through long dry periods, potentially centuries or longer, then reactivate during brief periods when liquid water appears. This strategy might allow life to survive, even on worlds where habitable conditions are rare and sporadic rather than continuous. Oligotrophs thrive in nutrient-poor environments where most life would starve. These organisms can extract energy and nutrients from resources that seem impossibly limited. Some bacteria derive energy from oxidizing trace amounts of hydrogen gas or from reducing tiny concentrations of metal ions. Others grow incredibly slowly, dividing perhaps once per century or even less frequently, living at the absolute minimum energy budget that can sustain life. These organisms survive in deep subsurface rocks, in ultra-pure cave water, and in nutrient-depleted ocean regions. The existence of oligotrophs suggests that life could persist in environments throughout the universe that seem too resource-poor to support metabolism. Deep beneath the surfaces of planets and moons, in the pores between rock grains, organisms might eke out existence on trace amounts of hydrogen from water-rock reactions, or on the minimal nutrients leached from minerals over geological timescales. This greatly expands the potential volume of habitable space, not just surfaces and oceans, but the entire crustal volume of rocky worlds down to depths where temperature becomes prohibitive. Some of the most extreme environments on Earth combine multiple stresses. Hydrothermal vents on the ocean floor experience high temperature, high pressure, high concentrations of toxic metals and sulfur compounds, and complete darkness. Yet these vents support thriving ecosystems based on chemosynthetic bacteria that extract energy from chemicals spewing from the vents. Hot acidic springs combine high temperature with extremely low pH. Ice-covered Antarctic lakes combine extreme cold with high salinity and seasonal or permanent darkness. Life found in these multi-stress environments proves that organisms can adapt to simultaneous challenges, not just single extremes. This ability to tolerate multiple stresses simultaneously is crucial for evaluating habitability on alien worlds, where conditions often involve several challenges at once. Europa's ocean experiences cold, pressure, darkness, and possibly high salinity, all at the same time. Mars's surface experiences extreme cold, desiccation, high radiation, and low pressure simultaneously. Venus's clouds experience high acidity, moderate temperature, and the presence of sulfuric acid droplets. Each of these environments might seem impossibly hostile when considered as a whole, but examining them as combinations of specific stresses that Earth organisms have individually overcome makes them seem more potentially habitable. The extremophiles of Earth demonstrate that life is far more flexible and resilient than once thought. Organisms have evolved mechanisms to survive and thrive in virtually every environment on Earth where liquid water exists, at least transiently, and where some source of chemical energy is available. Temperature, pressure, acidity, salinity, radiation, desiccation, each extreme that seems to represent an absolute barrier to life, turns out to be merely another challenge that evolution can overcome, given time and the right selection pressures. These discoveries transform our search for life beyond Earth. Rather than looking only for planets with Earth-like conditions, moderate temperature, neutral pH, low radiation, abundant water, we can expand our search to include extreme environments throughout the solar system and beyond. Volcanic hot springs on Mars or Venus, frozen oceans on icy moons, the clouds of Venus, subsurface aquifers deep within asteroids, the hydrothermal systems that might exist beneath the surfaces of large moons. All of these become potential habitats once we recognize that life on Earth already thrives in analogous extremes. The extreme environments where life could thrive extend from the scalding vents of volcanic springs to the frozen lakes of Antarctica, from the crushing depths of ocean trenches to the desiccated rocks of the driest deserts, from intensely acidic mine drainage to alkaline soda lakes, from the radiation-blasted rocks near nuclear waste to the nutrient-depleted waters of remote caves. Each extreme habitat on Earth hosts specialized organisms that have turned hostile conditions into homes through remarkable biochemical and physiological adaptations, proving that life's potential territory extends far beyond the comfortable middle ground to encompass nearly anywhere liquid exists, energy flows, and raw materials can be found. vastly expanding the cosmic real estate where life might emerge and flourish across the universe. The different types of habitable planets. When astronomers speak of habitable planets, they often mean worlds similar to Earth, rocky planets with liquid water on their surfaces, orbiting at comfortable distances from sun-like stars. But the discovery of thousands of exoplanets over the past few decades has revealed that planetary systems come in astonishing variety, with planet types that don't exist in our solar system and orbital configurations that defy early expectations. This diversity suggests that habitability, the capacity to support life, might extend far beyond Earth-like worlds to encompass planet types that seem alien at first glance, yet might provide suitable conditions for life to emerge and thrive. Understanding the different types of habitable planets means expanding our definition of habitability beyond the familiar, to consider the full range of worlds where biology might find a foothold. Ocean worlds represent perhaps the most common type of potentially habitable planet. These are planets covered entirely or nearly entirely by deep oceans, with no dry land or only minimal landmass protruding above water. Earth itself is an ocean world to some degree, with about 70% of its surface covered by water, but true ocean worlds might have water covering 95 or even 100% of the surface, with global oceans potentially hundreds of kilometers deep. Such worlds might form beyond the snowline in their stellar systems, where water ice is abundant during formation, then migrate inward to warmer regions where the ice melts, creating global oceans. Life on ocean worlds might never develop terrestrial forms. Everything would evolve in water, from microscopic plankton to potentially large swimming organisms analogous to whales. Without land, there would be no forests, no land animals, no terrestrial plants. But aquatic life could still be extraordinarily diverse and complex. The key question for ocean worlds is whether photosynthetic life could evolve. Sunlight penetrates only the upper layers of water, so photosynthesis would be restricted to the surface zone. Below a certain depth, life would depend on organic matter sinking from above, or on chemical energy from hydrothermal vents on the ocean floor, much like deep-sea ecosystems on Earth. Extremely deep oceans present another challenge: high-pressure ice. At depths exceeding several hundred kilometers, pressure can become so intense that water freezes despite high temperatures, forming exotic ice structures called Ice 6, Ice 7, and other high-pressure phases that are denser than liquid water. A planet with oceans deep enough to reach these pressures would have a layer of exotic ice separating the liquid ocean from the rocky mantle below. This ice layer would prevent direct contact between water and rock, potentially limiting the availability of minerals and nutrients dissolved from rock that life might need. However, the ice itself might crack due to tidal forces or internal heat, allowing some exchange between the rocky interior and the ocean. Desert planets represent the opposite extreme, worlds where water is scarce, with most of the surface covered by deserts, sand dunes, or bare rock. These planets orbit closer to the inner edge of the habitable zone, where temperatures are higher and water is more likely to evaporate. Any water present might be concentrated in polar ice caps, in subsurface aquifers, or in rare oases where geological features trap moisture. Mars represents a partial example, a cold desert world where water exists mostly as ice, or locked in minerals, with liquid water appearing only occasionally in specific locations. Life on desert planets would need extreme water conservation strategies. Organisms might be active only during rare rain events, spending most of their time dormant. They might extract water from humidity in the air or from chemical reactions rather than drinking liquid water. They might have impermeable skins to prevent water loss, and highly efficient kidneys or equivalent organs that recycle water internally. Plant analogues might photosynthesize only at night when temperatures drop and humidity rises, closing all pores during the day to prevent water loss. Despite the harsh conditions, life could potentially thrive in sheltered microenvironments, shaded canyons, caves where humidity condenses, or underground where water from ancient aquifers remains accessible. Eyeball planets emerge around red dwarf stars when planets become tidally locked, always showing the same face to their star, with one hemisphere in permanent daylight and the other in eternal darkness. The day side receives constant intense heating, potentially creating a hot desert. The night side, receiving no sunlight, freezes solid. But at the terminator, the boundary between day and night, a ring of habitable conditions might exist where temperatures remain moderate. This ring might harbour a circular ocean, the eyeball, surrounded by ice on one side and desert on the other, creating a narrow band where life could flourish. Life on eyeball planets would be restricted to this habitable ring, adapted to conditions that never change. No day-night cycle, no seasons, just constant twilight with the star permanently fixed at the horizon. Organisms might spread around the entire circumference of the planet along this habitable band, but they couldn't expand toward either pole. Moving toward the substellar point would lead to lethal heat. Moving toward the antistellar point would lead to frozen darkness. The planet's climate would feature constant winds as air heated on the day side rises and flows toward the cold night side, creating atmospheric circulation patterns completely unlike Earth's weather. Super-Earths, rocky planets more massive than Earth, but less massive than Neptune, might be the most common type of habitable planet in the galaxy, despite having no analogue in our solar system. These worlds, with masses ranging from about 2 to 10 times Earth's mass, would have stronger surface gravity than Earth. An organism on a super-Earth twice Earth's mass might weigh twice what it would on Earth, creating challenges for movement and structural support, but super-Earths have potential advantages for habitability. Their stronger gravity can hold thicker atmospheres more effectively, providing better greenhouse warming and allowing habitable zones to extend farther from their stars. They might have more active plate tectonics due to greater internal heat, helping regulate climate over geological time. Life on super-Earths would likely evolve shorter, stockier body plans to cope with high gravity. Trees might be shorter and thicker. Animals might have more legs or stronger, thicker legs to support their weight. Flight might be more difficult, requiring more powerful wings and muscles. But the thicker atmosphere might actually make flight easier by providing more air resistance, potentially allowing organisms to evolve gliding or flying capabilities using less energy than on Earth, despite the higher gravity. Mini-Neptunes, planets with substantial hydrogen-helium atmospheres surrounding rocky or icy cores, represent a planet type between rocky super-Earths and gas giants. These worlds might not be habitable at their cloud tops where temperatures and pressures are moderate, but atmospheres are thick hydrogen-helium mixtures. However, some mini-Neptunes might have layers within their atmospheres where temperature and pressure allow water vapor to condense into liquid water droplets, creating water clouds and potentially habitable conditions within the atmosphere itself. Aerial life in these water clouds, floating organisms that never touch solid ground because there is no solid ground accessible, might evolve. Such organisms would need to regulate their buoyancy, perhaps using gas-filled bladders similar to fish swim bladders. They might extract nutrients from atmospheric chemistry or from particles suspended in the atmosphere. Reproduction might involve releasing spores or offspring that drift through the atmosphere until they find suitable conditions to grow. The entire biosphere would be three-dimensional and airborne, with no connection to any surface. Hycean worlds, a term combining hydrogen and ocean, represent a recently proposed planet type that might be surprisingly common and habitable. These are large planets with hydrogen-rich atmospheres and liquid water oceans beneath them, potentially including some mini-Neptunes if conditions are right. The thick hydrogen atmospheres would create greenhouse warming that keeps water liquid even at large distances from the star. Life on Haitian worlds would live in the oceans beneath kilometers of hydrogen atmosphere, never exposed to space but potentially able to thrive in the dark, high-pressure water below. The discovery of biosignatures on Haitian worlds might be easier than on Earth-like planets because their larger sizes and extended atmospheres make spectroscopic analysis more favorable. If life produces gases that reach the hydrogen atmosphere, methane, dimethyl sulfide, or other organic compounds, these might be detectable even with current telescope technology. Haitian worlds thus represent prime targets for near-term biosignature searches. Carbon planets might form in regions of protoplanetary disks, where carbon is more abundant relative to oxygen than in our solar system. Instead of being dominated by silicate minerals like Earth, these worlds might have surfaces and interiors rich in graphite, diamond, silicon carbide, and other carbon compounds. The chemistry of such worlds would be radically different from Earth's. Oceans might consist of hydrocarbons, liquid methane, ethane, or more complex carbon compounds, rather than water. Life on carbon planets, if it evolved, would necessarily use chemistry adapted to carbon-rich, oxygen-poor conditions, potentially resembling the hydrocarbon-based biochemistry speculated for Titan. Lava worlds orbit so close to their stars that surface temperatures exceed the melting points of rock. These planets have surfaces of molten lava with atmospheres of vaporized rock, silicate gases that condense into mineral clouds and rain molten droplets. No life as we imagine it could survive on these surfaces, but some scientists speculate about exotic life existing in the upper atmosphere, where temperatures are lower, or about subsurface oceans trapped beneath the molten surface, where water remains liquid despite the hellish conditions above. Ice worlds covered by thick shells of water ice might be habitable not on their surfaces, which are frozen solid, but in subsurface oceans kept liquid by tidal heating from their parent planet's gravity. Jupiter's moon, Europa, and Saturn's moon, Enceladus, represent examples in our own solar system. Such worlds might be common around giant planets throughout the galaxy. The ice shell provides protection from radiation and impact, while the liquid ocean beneath could harbour extensive ecosystems based on chemical energy from hydrothermal vents rather than sunlight. These worlds would have dark biospheres, no photosynthesis, no dependence on their star, just chemosynthetic life, thriving in hidden seas. Rogue planets drifting through interstellar space with no star at all might still be habitable if they're massive enough to retain thick atmospheres that provide greenhouse warming through atmospheric pressure alone. A rogue Earth-mass planet with a very thick hydrogen atmosphere might maintain liquid water on its surface, despite receiving no starlight, heated only by residual internal radioactive decay and gravitational contraction. Life on such a world would exist in perpetual darkness, depending entirely on chemical energy and internal heat, completely independent of any star. A truly alien biosphere that could drift for billions of years through the void between stars. Binary planet systems where two similarly sized worlds orbit their common center of mass, like Pluto and Charon but potentially both habitable, might create unique conditions. Tidal forces between the planets would generate internal heating. The planets would raise tides on each other. If both have atmospheres, atmospheric circulation might be affected by the nearby companion. Life might evolve on both worlds simultaneously, potentially following different evolutionary paths, or life might spread from one to the other via meteorite impacts that eject material-carrying microorganisms between the two worlds. Trojan planets sharing the same orbit around a star, positioned at stable Lagrange, 0.60 degrees ahead of or behind each other, might exist in some systems. These planets would orbit at the same distance from their star, but would see each other as bright points in the sky, visible like particularly bright stars. If both are habitable, civilizations might arise on both, potentially detecting each other's presence long before achieving space travel, since the neighbouring world would be so prominent in their sky. The different types of habitable planets extend far beyond Earth analogues to encompass ocean worlds with global seas, desert planets with scarce water, tidally locked eyeball planets with habitable rings, massive super-Earths with strong gravity, aerial biospheres in thick atmospheres, subsurface oceans beneath ice shells, hydrocarbon-based chemistry on carbon planets, and rogue worlds wandering starless through the galaxy. Each type presenting unique challenges and opportunities for life, each potentially harbouring biospheres as rich and complex as Earth's, despite being profoundly different in their physical conditions, demonstrating that the cosmos might contain not just one type of living world, but a vast diversity of habitable environments where chemistry, energy, and time have combined to create the extraordinary phenomenon we call life, scattered across countless worlds in forms we're only beginning to imagine. How we measure the weight of space objects. When astronomers announce that Jupiter has more than 300 times Earth's mass, or that a distant black hole contains several billion times the Sun's mass, these numbers might seem impossibly precise. How can we possibly weigh objects millions or billions of miles away, objects we can never visit or touch, objects that are sometimes completely invisible? The answer lies not in direct measurement, but in observing how these objects interact gravitationally with their surroundings. Mass reveals itself through gravity, and by watching how objects move under gravitational influence, astronomers can calculate masses with remarkable accuracy using principles that Isaac Newton worked out more than 300 years ago. The fundamental principle is simple. The more massive an object is, the stronger its gravitational pull, and the faster other objects must move to orbit it. This relationship, encoded in Newton's law of universal gravitation and his laws of motion, allows us to determine mass from orbital motion. If you know how fast something orbits and how far away it is from the object it's orbiting, you can calculate the central object's mass. For planets in our solar system, we measure their masses by observing their moons. Jupiter has dozens of moons, and each one's orbital period and distance from Jupiter reveals Jupiter's mass. The formula is straightforward in principle. The orbital period squared is proportional to the orbital distance cubed divided by the central mass. By measuring the period and distance, we can solve for the mass. The more massive the central object, the faster moons must orbit at a given distance to avoid falling inward. Jupiter's moon Io orbits very close to Jupiter and completes an orbit in only about 42 hours. Because Jupiter's immense mass creates powerful gravity, our moon takes 27 days to orbit Earth at a similar distance, because Earth is much less massive than Jupiter. For planets without moons, Mercury and Venus, determining mass required more ingenuity. Before the space age, astronomers studied how these planets affected each other's orbits through their gravitational interactions. When two planets pass relatively close to each other, their gravitational pulls slightly deflect each other's paths. By precisely measuring these tiny perturbations over years of observations, astronomers could infer the masses of the planets involved. Space probes visiting these planets provided much more accurate mass measurements by observing how the planet's gravity affected the spacecraft trajectories. Measuring Earth's mass required understanding gravity itself. In the late 18th century, British scientist Henry Cavendish performed a delicate experiment using a torsion balance, a horizontal bar suspended by a thin wire with lead spheres at each end. By bringing large lead masses near the suspended spheres and measuring like the tiny twist in the wire caused by gravitational attraction, Cavendish determined the strength of gravity between known masses. This measurement, combined with the known acceleration of gravity at Earth's surface, allowed calculation of Earth's mass. The experiment is sometimes described as weighing the Earth, though it really measured how strongly Earth's gravity pulls compared to the gravity between laboratory masses. For the Sun, measuring mass is straightforward because Earth and all other planets orbit it. Earth orbits the Sun at a distance of about 150 million kilometers with an orbital period of 1 year. Plugging these numbers into the orbital equation gives the Sun's mass about 2 times 10 to the 30th power kilograms, or about 330,000 times Earth's mass. The exact same calculation works for any star with planets. Measure the planet's orbital distance and period, and you can determine the star's mass. Binary star systems, 2 stars orbiting each other, provide mass measurements for individual stars. By watching the stars orbit their common center of mass and measuring their orbital periods, distances, and velocities, astronomers can determine both stars' masses separately. This technique has measured thousands of stellar masses, revealing the relationship between a star's mass and its other properties like luminosity and temperature. These measurements show that stars range from about 8% of the Sun's mass for the smallest red dwarfs up to perhaps 150 times the Sun's mass for the most massive stars. For more distant objects, techniques become more sophisticated but still rely on gravitational effects. Galaxies contain hundreds of billions of stars, and measuring a galaxy's mass means measuring how fast stars and gas orbit within it. By observing the rotation speeds at different distances from the galactic center and applying the same orbital principles, astronomers can calculate the total mass enclosed within each radius. This technique revealed the existence of dark matter. The rotation speeds in the outer parts of galaxies are far too high to be explained by the visible stars and gas alone, requiring the presence of large amounts of invisible mass. Galaxy clusters, groups of hundreds or thousands of galaxies, have their masses measured through multiple techniques. One method observes the motions of individual galaxies within the cluster. The galaxies orbit within the cluster's gravitational potential, and their velocities reveal the cluster's total mass. Another technique uses gravitational lensing, the bending of light from more distant galaxies by the cluster's gravity. The amount of bending depends on the cluster's mass, so by measuring how background galaxies appear distorted, astronomers can map the cluster's mass distribution, including dark matter. Black holes present special challenges because they are invisible and often have no nearby objects in simple orbits. For stellar mass black holes in binary systems, astronomers measure the orbital motion of the visible companion star. The star's velocity and orbital period reveal the black hole's mass, even though the black hole itself emits no light. This technique confirmed that several X-ray binary systems contain objects too massive to be neutron stars. They must be black holes. Supermassive black holes at galaxy centers are weighed by observing stars or gas orbiting near them. The Milky Way's central black hole, Sagittarius A star, has its mass measured precisely by tracking individual stars as they orbit. One star, designated S2, completes an orbit every 16 years in an elongated ellipse that brings it within about 120 times Earth's distance from the Sun, extremely close by galactic standards. By measuring S2's position and velocity throughout its orbit, astronomers calculated the black hole's mass at about 4 million times the Sun's mass. This measurement is accurate to within a few percent, despite the black hole being 26,000 light-years away. More distant supermassive black holes are measured through the motion of stars or gas closer to the black hole than telescopes can individually resolve. Instead, spectroscopy measures the range of velocities present in the light coming from the galaxy's central region. Broader velocity distributions indicate faster-moving material, which requires more mass to keep the material bound. Using this technique, astronomers have measured black hole masses ranging from millions to billions of solar masses in galaxies across the universe. Gravitational waves from merging black holes provide another mass measurement technique. When two black holes spiral together and merge, they emit gravitational waves, ripples in space-time itself, detected by observatories like LIGO. The frequency and amplitude of these waves encode information about the black hole's masses. The first gravitational wave detection, in 2015, came from two black holes weighing about 29 and 36 solar masses that merged into a single black hole of about 62 solar masses, with 3 solar masses worth of energy radiated away as gravitational waves during the collision. For objects we can visit with spacecraft, mass measurements become more direct. The spacecraft's trajectory bends as it passes the object, with the deflection determined by the object's mass. By tracking the spacecraft's position using radio signals and measuring the Doppler shift in those signals, mission controllers determine the trajectory precisely. Comparing the observed trajectory to computer models reveals the mass that must have caused that particular deflection. This technique has measured masses of asteroids, comets, and moons with no satellites of their own. Small asteroids present particular challenges. Without satellites, and too small to significantly affect spacecraft at typical flyby distances, their masses remained uncertain until spacecraft flew very close or even orbited them. The near-Shoemaker spacecraft orbited asteroid Eros for a year, precisely measuring Eros's mass and density. The Hayabusa and OSIRIS-REx missions orbited small asteroids, Ryugu and Bennu respectively, measuring their masses through orbital mechanics and revealing that both asteroids are loose rubble piles rather than solid rocks. The precision of mass measurements varies enormously. The Sun's mass is known to about 7 significant figures. Earth's mass is known even more precisely because we can measure Earth's gravitational field from satellites in low orbit. Jupiter's mass is known very precisely from spacecraft tracking, but the mass of a distant galaxy might be uncertain by 10 or 20%, and masses of galaxy clusters can be uncertain by even more, particularly if dark matter doesn't follow the same distribution as visible matter. Understanding the limitations matters. When astronomers quote a mass, there's always uncertainty attached. Reporting that a black hole contains about 4 million solar masses acknowledges this uncertainty. The actual value might be 3.8 million or 4.2 million, and that range represents our measurement precision, not variability in the black hole's mass. All these techniques ultimately trace back to gravity, the fundamental force that governs how massive objects interact across space. Mass creates gravity, gravity creates motion, and by observing that motion precisely, we can work backward to determine the mass that caused it. From moons orbiting planets, to galaxies orbiting within clusters, from binary stars wheeling around each other, to stars orbiting supermassive black holes, the cosmos is filled with objects whose motions reveal the masses of the bodies that control them. By watching these cosmic dances and applying the mathematical laws that Newton first articulated, astronomers can weigh objects from the smallest asteroids to the largest galaxy clusters, measuring masses across a range spanning more than 20 orders of magnitude. From asteroids weighing billions of tons to galaxy clusters weighing millions of trillions of times more than the Sun, all without ever placing these objects on a scale, relying instead on the universal language of gravity that connects everything in the cosmos through the elegant mathematics of orbital motion. The bright and dark features on surfaces. Across the solar system, the surfaces of planets, moons, and asteroids display remarkable contrasts between light and dark regions. These variations in brightness, called albedo features, paint cosmic bodies with patterns that range from subtle shadings to stark contrasts, each telling a story about composition, geology, and the forces that have shaped these worlds over billions of years. Consider Earth's moon, the most familiar example. Even without a telescope, you can see the dramatic difference between the bright highlands and the dark Maria, the ancient lava plains that early observers mistook for seas. The bright regions are ancient crust formed over 4 billion years ago when the moon was young and its surface was still cooling from a molten state. This primordial crust is rich in a mineral called anorthosite, a type of rock that's relatively light in colour and highly reflective. These highlands are the original surface of the moon, battered by eons of meteorite impacts, but still retaining their pale character. The dark Maria formed later, between about 3.8 and 3.1 billion years ago, when massive asteroid impacts punched through the moon's crust and allowed molten rock from the interior to flood onto the surface. This lava was basaltic, similar to the lava that flows from volcanoes in Hawaii, and it's much darker than the highland material. The basalt contains more iron and magnesium than the ancient crust, and these elements absorb more light, giving the Maria their characteristic dark appearance. When this lava cooled and solidified, it created vast, smooth plains that still dominate the near side of the moon today. The moon's far side presents a different face, with far fewer dark Maria and much more bright highland terrain. This asymmetry puzzled scientists for decades. Why would one side of the moon have so much volcanic flooding, while the other side remained mostly ancient highland? The answer lies in the moon's structure. The crust on the far side is thicker, making it harder for lava to break through, even when massive impacts occurred. The near side's thinner crust allowed molten rock to more easily reach the surface, creating the face we see each night. Mars displays its own dramatic albedo patterns, visible even through small telescopes from Earth. The planet shows bright regions and dark regions that early astronomers mapped and named, imagining them to be continents and seas. The bright areas are primarily ancient highland regions, covered with fine dust that's rich in iron oxide, essentially rust, giving Mars its characteristic red colour. This dust is incredibly fine, almost like talcum powder, and it reflects sunlight fairly efficiently despite its red hue. The dark regions on Mars are areas where the dust has been blown away by winds, exposing darker underlying rock or concentrations of dark sand. Some of these features change over time as seasonal winds redistribute dust across the planet's surface. During global dust storms, which can envelope the entire planet, the contrast between bright and dark features diminishes as everything gets covered in suspended dust. As the storm settles, the patterns gradually re-emerge, though sometimes in slightly different configurations than before. One of Mars's most prominent dark features is Syrtis Major, a broad shield volcano whose dark basaltic rock stands in stark contrast to the surrounding bright highlands. This feature was one of the first to be recognized on Mars and has been used for centuries to track the planet's rotation. The dark rock here is volcanic in origin, similar to the moon's Maria, and it resists being covered by the bright dust that blankets much of the planet. Mercury, the innermost planet, shows subtle but distinct albedo variations across its heavily cratered surface. The overall planet is fairly dark, reflecting only about 12% of the sunlight that hits it, making it one of the least reflective rocky bodies in the solar system. But within this generally dark surface, brighter and darker regions exist. Some craters have bright rays extending from them, where the impact that formed the crater excavated fresher material from beneath Mercury's space-weathered surface and scattered it across the surrounding landscape. The darker regions on Mercury include vast, smooth plains that, like the moon's Maria, formed when lava flooded the surface billions of years ago. But Mercury also has mysterious dark material that appears to have been deposited from volcanic eruptions in a more explosive fashion. This dark material, which may be rich in carbon or other volatile rich compounds, creates some of the darkest features on the planet's surface, appearing almost black in high-resolution images. Jupiter's moon Europa presents one of the most striking albedo contrasts in the solar system. The moon's surface is almost entirely water ice, but it's not uniformly bright. The cleanest ice is brilliantly white, reflecting nearly all the sunlight that touches it. But cutting across this bright surface are countless dark lines and streaks, forming patterns that remind observers of cracks in pack ice on Earth. These dark features are ridges and bands where the ice has fractured and material from beneath, perhaps salts, sulfur compounds, or organic molecules, has been exposed or deposited on the surface. Some of Europa's dark features appear reddish-brown, suggesting the presence of salts like magnesium sulfate or sodium chloride that have been altered by radiation from Jupiter's intense magnetic field. The radiation breaks apart molecules and creates new compounds, darkening and discoloring the surface materials over time. The brightest regions on Europa are thought to be the youngest, places where fresh ice has recently been exposed or deposited, while the darker, more discolored regions are older surfaces that have been exposed to radiation for longer periods. Saturn's moon Iapetus displays perhaps the most dramatic albedo contrast of any body in the solar system. One hemisphere is as bright as fresh snow, reflecting about 60% of incoming sunlight, while the other hemisphere is as dark as asphalt, reflecting only about 4%. The boundary between these regions is sharp and striking, creating an appearance that reminded astronomers of a yin-yang symbol. The dark material, concentrated primarily on the leading hemisphere, the side that faces forward as Iapetus orbits Saturn, may have originated from dark dust in Saturn's system that Iapetus swept up as it moved through space, or it may have erupted from the moon's interior through cryovolcanic processes. Once the initial dark material was deposited, a feedback process likely amplified the contrast. Dark surfaces absorb more sunlight and heat up more during the day. On Iapetus, where daytime temperatures can reach as high as -230 degrees Fahrenheit in sunny areas, this slight extra heating in the dark regions causes water ice to slowly sublimate, transition directly from solid to vapor. This water vapor migrates to colder regions, including the bright trailing hemisphere, where it refreezes. Over millions of years, this process has darkened the dark hemisphere further by removing its ice and brightened the bright hemisphere by depositing additional ice there. Pluto, visited by NASA's New Horizons spacecraft in 2015, revealed a surface of surprising complexity and dramatic albedo contrasts. The dwarf planet's most prominent dark feature, informally named Cthulhu Regio, is a vast region near the equator that appears deep red-brown in colour. This dark material is thought to be complex organic molecules called tholins, formed when ultraviolet light from the distant sun and cosmic rays interact with methane and nitrogen in Pluto's thin atmosphere. These molecules rain down onto the surface, accumulating over time and creating the dark coloration. Adjacent to this dark region lies Sputnik Planitia, a vast plain of bright nitrogen ice that forms the western lobe of Pluto's heart-shaped feature. This bright ice reflects much more light than the surrounding terrain. The contrast exists because nitrogen ice is relatively bright and because this region is geologically active. The ice is constantly churning in slow convection cells, bringing fresh material to the surface and preventing the accumulation of the dark organic compounds that colour other parts of Pluto. Asteroids show their own albedo variations, though measuring them requires careful observation. Some asteroids are quite dark, reflecting only 3 or 4% of the light that hits them. These are typically carbonaceous asteroids, rich in carbon compounds and hydrated minerals, making them among the darkest natural objects known. Other asteroids are much brighter, particularly those made primarily of metal or rocky silicates. The contrast between dark and bright asteroids tells scientists about their composition and helps trace them back to different regions of the early solar system where they formed. Even within a single asteroid, albedo features can exist. Some asteroids show bright spots that might be exposed fresh material where an impact has recently broken through a darkened space-weathered surface layer. Others show variations that might indicate different minerals or rock types at the surface. The asteroid Vesta, one of the largest in the main belt, shows dramatic brightness variations across its surface, with some regions nearly twice as reflective as others. The process called space weathering affects the brightness of surfaces throughout the solar system. When cosmic rays, solar wind particles, and micrometeorites bombard a surface over time, they gradually darken it and change its reflective properties. Fresh surfaces, recently exposed by impacts or other processes, appear brighter. Ancient surfaces that have been exposed to space for billions of years generally appear darker and redder than they would if the same material were fresh. On the Moon, this space weathering creates the subtle variations in brightness visible within both the highlands and the Maria. The rays around young craters appear bright because the impact has excavated fresh material. Over hundreds of millions of years, these rays gradually fade as space weathering darkens the ejected material, causing it to blend in with the surrounding ancient terrain. Comets show extreme albedo contrasts as well. The nucleus of a comet, the solid body beneath the gas and dust, is among the darkest objects in the solar system, often reflecting only about 4% of incident light. This dark material is thought to be a mixture of organic compounds, similar to the tholins on Pluto, mixed with dust and ice. But when a comet approaches the Sun and begins to release gas and dust, it can develop bright areas where fresh ice is exposed and actively sublimating, creating jets of gas that appear much brighter than the surrounding dark nucleus. The study of albedo features requires careful measurement. Scientists use photometry to measure exactly how much light a surface reflects at different wavelengths. By comparing the brightness at different wavelengths, they can determine not just whether a surface is bright or dark overall, but what specific materials might be present. Iron-rich minerals absorb light differently than ice, which absorbs differently than sulfur compounds or organic materials. Each substance has its own spectral signature, revealed through its albedo characteristics. These patterns of light and dark across the surfaces of solar system bodies are not mere decoration. They are maps written in brightness, showing us where different materials exist, where geologic processes have been active, where impacts have occurred, and how surfaces age under the constant bombardment of radiation and particles from space. Every bright crater ray, every dark lava plain, every reddish streak of organic material tells part of the story of how these worlds formed and evolved, creating the complex and beautiful patterns we observe across the solar system. The crystal-like structures in space, deep within the cosmos, far from the warmth of any star, materials arrange themselves into patterns that would look familiar under a microscope on Earth. These crystalline structures form in the most unexpected places, defying the assumption that space is simply a chaotic void of random particles and radiation. In the cold depths between stars, water molecules slowly drift together, each one eventually finding its place in an organized lattice. The process happens atom by atom, molecule by molecule, as temperatures hover just a few degrees above absolute zero. Unlike the rapid freezing we experience on Earth, these ice crystals have time, millions of years sometimes, to achieve near-perfect geometric arrangements. The hexagonal patterns repeat endlessly, creating structures that catch and reflect starlight in particular ways that astronomers can detect from across the galaxy. Silicate minerals also crystallize in space, forming within the cooling outflows of dying stars. As a red giant sheds its outer layers, temperatures drop from thousands of degrees to just hundreds, creating conditions where molten rock can slowly solidify into crystals. These aren't the rough, irregular chunks we might expect. They're often perfectly formed olivine crystals, the same green mineral found in beach sand on Earth, but floating freely in the vacuum between worlds. Some of these crystals are microscopic, barely larger than the wavelength of light, while others grow to sizes that would be visible to the naked eye if you could somehow hold one. The environment around young stars presents another laboratory for crystal formation. In the swirling disk of gas and dust that will eventually become planets, temperatures vary dramatically with distance from the central star. There's a boundary, a line in space, where water transitions from gas to solid ice. Scientists call this the snow line or ice line, and it's here that water crystallizes directly from vapor without ever being liquid. The crystals that form are often elaborate, with branching structures that would rival any snowflake on Earth. These become the building blocks of comets and the icy cores of giant planets. Carbon takes on crystalline forms in space as well. In the hearts of ancient stars where pressures and temperatures reach extremes, carbon atoms arrange themselves into diamond structures. These aren't the large gemstones of jewelry stores, but microscopic grains that get expelled into space when the star dies. Scientists have found these pre-solar diamonds in meteorites that have fallen to Earth, tiny time capsules that formed before our solar system even existed. Each one contains isotope ratios that don't match anything that formed near our sun, proving they crystallized around entirely different stars. The surfaces of comets hide their own crystalline secrets. When these icy bodies spend long periods in the cold outer reaches of the solar system, the water ice in them gradually transitions from an amorphous glass-like state into a crystalline form. This transition releases trapped gases, sometimes causing the comet to briefly become more active, even when it's far from the sun. The crystalline ice has a different density than the amorphous ice, creating stresses within the comet's structure that can cause chunks to break away. Methane ice crystallizes on the surfaces of distant worlds, like Pluto and Neptune's moon Triton. At the frigid temperatures found in the outer solar system, methane behaves much like water ice does on Earth. It forms mountains and plains, fills craters, and even creates frost that glitters on the surface. The crystal structure of methane ice determines how it flows and breaks, shaping these distant landscapes in ways that mirror glacial processes on Earth, but with a completely different material. Salt crystals have been detected in the geysers of Saturn's moon Enceladus. Deep beneath this tiny world's icy crust lies an ocean of liquid water, kept warm by tidal heating from Saturn's gravity. When water from this ocean erupts through cracks in the ice, it immediately begins to freeze in the vacuum of space. But before it freezes completely, dissolved salts precipitate out, forming tiny crystalline particles that get ejected into space along with the ice. These salt crystals tell scientists about the chemistry of that hidden ocean. In the dusty clouds where stars form, silicate grains develop crystalline structures that affect how they interact with light and heat. When these grains are hit by shockwaves from nearby stellar explosions, the intense but brief heating can transform their atomic structure, creating crystals with specific properties. The type of crystal that forms depends on the exact composition of the grain and the intensity of the heating event. Some become forsterite, a magnesium-rich crystal that glows warmly in infrared light. Others become enstatite, a pyroxene mineral with a different crystal lattice. The process of crystallization in space isn't always slow and gradual. Sometimes it happens in moments. When two white dwarf stars collide, the tremendous pressures and temperatures can cause carbon to crystallize almost instantaneously into diamond. The resulting object might have a core of crystallized carbon surrounded by layers of other materials, a cosmic gemstone larger than our Earth itself, hidden from view by its outer envelope. Amino acids, the building blocks of proteins, have been found in meteorites in crystalline forms. These organic crystals formed in the cold of space, where complex molecules could arrange themselves into ordered structures. The handedness of these crystals, whether they twist to the left or right, has implications for how life might have begun on Earth. the predominance of certain crystal orientations in space-formed amino acids might explain why life on Earth uses left-handed amino acids almost exclusively. Iron and nickel alloys crystallize in the cores of asteroids, forming structures called Widmanstätten patterns. These form when molten metal cools extraordinarily slowly over millions of years, allowing different crystal phases to separate and create geometric patterns. When metallic meteorites are cut, polished, and etched with acid, these patterns become visible as interlocking crystals that look almost like abstract art. The size and arrangement of these crystals tell scientists about the thermal history of the asteroid they came from. Sulfur compounds crystallize on the surface of Jupiter's moon, Io, the most volcanically active body in the solar system. The sulfur takes on different crystalline forms depending on temperature, creating a multicolored landscape of yellows, reds, oranges, and whites. Each color represents a different allotrope of sulfur, a different way the atoms can arrange themselves into crystal structures. These crystals don't last long in their original form. The intense radiation from Jupiter and the constant volcanic resurfacing mean that sulfur crystals are continually forming, breaking down, and reforming. In the coldest clouds of interstellar space, carbon dioxide freezes into dry ice crystals. These crystals coat the surfaces of dust grains, creating icy mantles that change how the grains interact with each other and with radiation. The crystal structure of this frozen carbon dioxide determines how easily it can trap other molecules, creating complex ices that contain dozens of different compounds, all organized in crystalline matrices. Phosphates and other minerals crystallize in meteorites under conditions that never occur on Earth today. These crystals preserve information about the early solar system, including the presence of water and the temperatures that existed on their parent asteroids. Some contain tiny pockets of liquid water trapped within the crystal structure, water that has been sealed away for over 4 billion years. The magnetic minerals in meteorites show evidence of crystallization in the presence of magnetic fields. The way iron oxide crystals align as they form reveals information about magnetic fields that existed around the young sun and in the interiors of molten asteroids. These crystals act as fossil compasses, recording ancient magnetic environments that have long since disappeared. Quartz crystals, so common on Earth, form in space as well, though through different processes. In the shocked material around impact sites, the intense pressure can cause silicon and oxygen to crystallize into quartz with unusual properties. Some of these crystals contain defects and inclusions that could never form under Earth's surface conditions, making them distinct markers of extraterrestrial origin. The study of crystalline structures in space reveals that the same fundamental physics that governs crystal formation in earthly laboratories operates throughout the universe. Temperature, pressure, chemical composition, and time determine what forms, but the basic rules remain constant whether the crystals form in a laboratory, deep in the Earth, or in the cold expanse between stars, where matter continues to organize itself into patterns of surprising complexity and beauty. The invisible forces holding galaxies together. When you look at a photograph of a spiral galaxy, you see a beautiful pinwheel of stars, gas, and dust rotating around a central bulge. The image suggests a structure held together by visible matter, the billions of stars whose light creates the galaxy's luminous form. But appearances are deceiving. The forces actually holding galaxies together are largely invisible, operating through mechanisms both understood and mysterious. Gravity binds these cosmic structures, but most of the mass providing that gravity cannot be seen, cannot be detected except through its gravitational effects, and remains one of the deepest mysteries in astrophysics. The first clue that something invisible was holding galaxies together came from studying how stars move within them. In the 1970s, astronomer Vera Rubin conducted detailed observations of spiral galaxies, measuring the velocities of stars and gas clouds at various distances from the galactic centers. According to Newton's laws of motion and gravity, objects farther from the center of mass should orbit more slowly, just as Neptune orbits the Sun much more slowly than Mercury. The visible matter in galaxies is concentrated toward the center, with the brightness falling off dramatically in the outer regions. Based on this distribution of visible matter, stars in the outer parts of galaxies should be moving much slower than stars near the center. But that's not what Rubin found. Instead, the rotation curves, graphs showing orbital velocity versus distance from the center, were flat. Stars in the outer regions were moving just as fast as stars closer to the center, sometimes even faster. This could only mean one thing. There was far more mass in these galaxies than could be accounted for by visible stars, gas, and dust. This additional mass had to extend well beyond the visible disk, forming a massive spherical halo surrounding each galaxy. The nature of this dark matter remains unknown, but its gravitational effects are undeniable. Galaxies are embedded within dark matter halos that contain several times more mass than all the visible matter combined. A typical spiral galaxy, like the Milky Way, might contain about 100 billion solar masses of visible matter, stars, gas, dust, planets, but resides within a dark matter halo containing perhaps 1 trillion solar masses. This dark matter halo extends perhaps 10 times farther than the visible disk, creating a gravitational well that holds the galaxy together. Dark matter doesn't interact with light. It neither emits, absorbs, nor reflects electromagnetic radiation of any wavelength. It interacts with normal matter almost exclusively through gravity. This makes it invisible to telescopes, but reveals its presence through gravitational effects. The flat rotation curves that Rubin observed were the first clear evidence, but dark matter reveals itself in other ways as well. Gravitational lensing provides some of the most compelling evidence for dark matter in and around galaxies. According to Einstein's general theory of relativity, mass warps spacetime, and light follows the curves in that warped geometry. When light from a distant galaxy passes near a massive object, its path bends. By measuring this bending and calculating how much mass would be needed to produce it, astronomers can map the distribution of mass, including dark matter. These mass maps show that dark matter is distributed in huge halos around galaxies, exactly as predicted from rotation curve studies. The bullet cluster provides particularly dramatic evidence. This structure formed when two galaxy clusters collided and passed through each other. During the collision, the hot gas from each cluster, normal matter that can interact with itself, slowed down and remained near the collision site, heated by the impact. But gravitational lensing maps show that most of the mass is not where the gas is. Instead, it separated from the gas and continued moving with the galaxies themselves. This separated mass must be dark matter, which doesn't collide or interact with normal matter except through gravity, passing right through during the cluster collision. The gravitational force from dark matter operates according to Newton's law of universal gravitation for most purposes, though general relativity provides the more accurate description, especially in strong gravitational fields. The force is proportional to the product of the masses and inversely proportional to the square of the distance between them. Even though individual dark matter particles don't clump together the way atoms do, they can't radiate energy and settle into compact structures. Collectively, they form halos through gravitational attraction, with each particle orbiting in the combined gravitational field of all the others. These dark matter halos formed before the visible galaxies themselves. In the early universe, dark matter could begin collapsing into clumps earlier than normal matter, because dark matter doesn't interact with radiation. Normal matter coupled to photons in the early universe, couldn't collapse efficiently until after recombination, when electrons combined with nuclei to form neutral atoms and the universe became transparent. By that time, dark matter had already created gravitational wells, regions of enhanced density, and normal matter fell into these wells, forming the first galaxies within the scaffolding of dark matter structure. Computer simulations of galaxy formation must include dark matter to reproduce the observed properties of galaxies. Simulations using only normal matter produce galaxies that look nothing like what we observe. But when dark matter is included, with properties consistent with observations, non-interacting except through gravity, with a specific abundance relative to normal matter, the simulations produce galaxies remarkably similar to real ones, with flat rotation curves, realistic sizes, and appropriate clustering properties. The dark matter distribution within galaxies follows a characteristic profile. The density is highest at the center and decreases toward the outer regions, but much more gradually than the distribution of visible matter. Various mathematical models describe this distribution, with names like the NFW profile, named after Julio Navarro, Carlos Frenk, and Simon White, who studied dark matter halos in simulations in the 1990s. These profiles predict specific density distributions that can be tested against observations through rotation curves and gravitational lensing. But dark matter isn't the only force holding galaxies together. Gravity from visible matter contributes as well, though less than dark matter. The combined gravitational pull from billions of stars, gas clouds, dust, and the supermassive black hole at the center all help bind the galaxy. The distribution of this visible matter creates the gravitational potential in which stars orbit, and while dark matter dominates the total mass, the visible matter shapes the inner regions where most stars reside. Orbital mechanics plays a crucial role in keeping galaxies stable. Each star orbits in the combined gravitational field of all other matter in the galaxy, both visible and dark. Stars don't simply circle the galactic center in perfect circles like planets orbiting the Sun. Their orbits are more complex, elliptical, and tilted at various angles, creating the three-dimensional structure of the galaxy. In spiral galaxies, the disk forms because stars that were born from a rotating cloud of gas inherited that rotation, and collisions between gas particles dissipated energy and flattened the distribution into a disk. The supermassive black hole at the center of most galaxies contributes to holding the inner regions together, though its mass is typically small compared to the total galaxy mass, perhaps 0.1 to 1% of the bulge mass. The black hole at the center of the Milky Way, Sagittarius A star, contains about 4 million solar masses. While this is enormous by any terrestrial standard, it's tiny compared to the Milky Way's total mass of perhaps 1 trillion solar masses, including dark matter. The black hole's gravitational influence dominates only in the innermost few light years. Spiral density waves also play a role in galactic structure, though they're not forces holding the galaxy together in the same sense as gravity. These waves are regions of enhanced density that rotate through the disk, compressing gas and triggering star formation. The spiral arms we see are not fixed structures, with the same stars always in them, but rather patterns that rotate at a different speed than the stars themselves. Stars move in and out of the spiral arms as they orbit, spending more time in the arms where the density is higher, creating the appearance of persistent spiral structure. Galaxy clusters add another layer of complexity. Galaxies themselves are held together primarily by their dark matter halos, but galaxies cluster together in groups and clusters, which are themselves held together by even larger dark matter halos. The Milky Way is part of the local group, which includes the Andromeda Galaxy and about 50 smaller galaxies, all orbiting within a common dark matter halo. galaxy clusters, like the Virgo cluster, contain thousands of galaxies within a massive dark matter halo containing quadrillions of solar masses. The dynamical state of galaxies, whether they're stable, expanding, or contracting, depends on the balance between kinetic and potential energy. If the kinetic energy of all the stars and gas exceeds twice the magnitude of the gravitational potential energy, the galaxy would be unbound and would eventually fly apart. The fact that galaxies remain bound over billions of years tells us that they're in virial equilibrium, a state where kinetic and potential energy are balanced according to the virial theorem. This relationship allows astronomers to estimate the total mass of galaxies from observations of how fast their contents are moving. Some alternative theories propose that dark matter doesn't exist, and that instead, our understanding of gravity needs modification. Modified Newtonian dynamics, or MOND, proposed by Mordechai Milgram in 1983, suggests that gravity behaves differently at very low accelerations, like those experienced by stars in the outer regions of galaxies. MOND can reproduce flat rotation curves without dark matter, but it struggles to explain other observations like gravitational lensing and the bullet cluster. Most physicists consider dark matter more likely to be a new type of particle rather than a modification of gravity, though the question remains open until dark matter is directly detected or conclusively ruled out. The search for dark matter particles continues in laboratories around the world. Experiments deep underground attempt to detect rare interactions between dark matter particles and normal matter. Other experiments search for signals of dark matter particles annihilating with each other or decaying into detectable particles. The Large Hadron Collider attempts to create dark matter particles in high-energy collisions. So far, no experiment has definitively detected dark matter particles, but each null result constrains the possible properties of dark matter, narrowing the possibilities. The invisible forces holding galaxies together operate on timescales of hundreds of millions to billions of years. A star near the Sun's position in the Milky Way takes about 225 million years to complete one orbit around the galactic center. During this time, the combined gravitational pull from the dark matter halo, the visible matter in the disk and bulge, and all other components keeps the star bound to the galaxy. The stability of this configuration over billions of years, galaxies don't fly apart, they maintain their structures over cosmic time, testifies to the power and precision of the gravitational forces at work. Understanding the invisible forces holding galaxies together remains one of the central challenges in astrophysics. The existence of dark matter is now accepted by most scientists based on the overwhelming gravitational evidence, but its fundamental nature remains mysterious. Whether it consists of weakly interacting massive particles, axions, primordial black holes, or something entirely unexpected, dark matter's gravitational pull provides the invisible glue that holds galaxies together, shapes their structure, determines their evolution, and creates the cosmic web of large-scale structure that defines the universe on the largest scales, making dark matter's invisibility one of the most tantalizing mysteries in science, a substance that makes up most of the universe's mass, but reveals itself only through the ancient and universal force of gravity that governs the motion of everything, from falling apples to orbiting galaxies. The chemistry required for life beyond Earth. Life at its most fundamental level is chemistry. Every thought you think, every breath you take, every movement you make results from chemical reactions occurring in your cells. Molecules bind together and break apart, energy flows from one form to another, and through countless chemical transformations, inanimate matter becomes animate. Dead molecules become living organisms. Understanding what chemistry is required for life beyond Earth means understanding what makes life possible at all. The elements, the reactions, the solvents, and the energy sources that could allow chemistry to cross the threshold from complex but lifeless reactions into something that grows, reproduces, evolves, and ultimately builds civilizations among the stars. Carbon stands at the center of all known life. Every organism on Earth, from bacteria to blue whales, builds its body from carbon-based molecules. Carbon's unique properties make it extraordinarily suitable for life. Each carbon atom can form 4 chemical bonds with other atoms, allowing it to create an immense diversity of molecular structures: long chains, branching trees, rings, and complex 3-dimensional shapes. Carbon bonds with itself strongly enough to create stable molecules, but not so strongly that the bonds cannot be broken and rearranged through normal chemical reactions. This balance allows carbon molecules to be both stable enough to maintain structure and reactive enough to participate in the constant chemical transformations that life requires. Organic chemistry, the chemistry of carbon compounds, encompasses millions of known molecules and potentially billions more that could exist. Carbon combines readily with hydrogen, oxygen, nitrogen, sulfur, and phosphorus to create the molecules of life. Proteins, the workhorses of cells that catalyze reactions and build structures, are chains of amino acids linked together, each amino acid containing carbon, hydrogen, oxygen, and nitrogen. DNA and RNA, which store and transmit genetic information, are built from carbon-containing sugars, phosphate groups, and nitrogen-rich bases. Lipids, which form cell membranes and store energy, are long carbon chains with various functional groups attached. Carbohydrates, which provide energy and structural support, are carbon molecules with hydrogen and oxygen in specific ratios. But is carbon truly necessary for life, or is it simply the element that happened to work on Earth? Silicon, sitting directly below carbon in the periodic table, shares many of carbon's properties. Silicon also forms 4 chemical bonds and can create chains and rings similar to carbon. Science fiction has long speculated about silicon-based life, but silicon faces significant challenges. Silicon-silicon bonds are weaker than carbon-carbon bonds, making long silicon chains less stable. Silicon compounds tend to be much less diverse than carbon compounds. While carbon forms millions of different molecules, silicon chemistry is far more limited. Most critically, silicon's most common compound is silicon dioxide, quartz, sand, rock, which is extremely stable and insoluble. When silicon burns with oxygen, it creates solid rock rather than a gas that can be easily expelled and recycled. However, silicon-based life might be possible in environments completely unlike Earth. In extremely cold environments where water is frozen solid, silicon chemistry might become more favorable. In the presence of liquid hydrocarbons instead of water, silicon compounds might behave differently, remaining soluble and reactive rather than precipitating as rocks. A frigid world with seas of liquid methane or ethane, like Saturn's moon Titan, might provide conditions where silicon-based biochemistry could operate. Such life would function on completely different principles than Earth's carbon-based organisms, but it might still meet the basic requirements: complexity, self-replication, evolution, and metabolism. Hydrogen plays a crucial role in biochemistry beyond being part of organic molecules. Hydrogen ions, protons, are essential for energy generation in cells. Earth's organisms create differences in hydrogen ion concentration across membranes, then allow the ions to flow back through specialized proteins called ATP synthase, which harness the flowing ions to create ATP, the universal energy currency of life. This process, called chemiosmosis, powers nearly all life on Earth and represents a fundamental way of coupling energy sources to useful work. Any biochemistry, whether carbon-based or otherwise, would need some mechanism for capturing and storing energy, and hydrogen's simple chemistry makes it an excellent candidate for this role, regardless of the specific biochemistry involved. Oxygen serves multiple roles in Earth's biochemistry. It's part of water, part of most organic molecules, and it serves as the final electron acceptor in cellular respiration, the process by which organisms extract energy from food. When glucose is metabolized with oxygen, the reaction releases large amounts of energy that cells capture in the chemical bonds of ATP. This oxygen-based metabolism, called aerobic respiration, is far more efficient than metabolism without oxygen. However, oxygen was not always available on Earth. For the first 2 billion years or more, Earth's atmosphere contained very little free oxygen, and early life functioned without it, using anaerobic metabolism based on different chemical reactions. Some organisms today still live without oxygen, in deep ocean sediments or the guts of animals, using sulfur compounds, nitrates, or iron as alternatives to oxygen. Life beyond Earth might never develop oxygen-based metabolism if oxygen never becomes abundant in the atmosphere. Planets orbiting red dwarf stars might have difficulty accumulating oxygen because ultraviolet light from the star, which on Earth helps break apart water molecules in the upper atmosphere, leading to oxygen accumulation, is less intense. Life on such worlds might remain dependent on anaerobic metabolism indefinitely, which would likely limit the size and energy consumption of organisms. Active, energy-intensive lifestyles, like those of birds or mammals, require the high energy output that only oxygen metabolism provides. Alien life using alternative metabolic pathways might be restricted to smaller, slower, lower energy forms. Nitrogen is essential for proteins and nucleic acids. It's found in amino acids and in the bases that make up DNA and RNA. Nitrogen chemistry is complex and often difficult. Nitrogen gas in the atmosphere consists of 2 nitrogen atoms triple bonded together, making it very stable and unreactive. Converting atmospheric nitrogen into biologically useful forms, a process called nitrogen fixation, requires significant energy or specialized catalysts. On Earth, certain bacteria can fix nitrogen using enzymes containing iron and molybdenum. Lightning also fixes nitrogen by forcing nitrogen and oxygen to react in the high-energy conditions of electrical discharge. Life on other planets would need some source of biologically available nitrogen, either through similar fixation processes or through nitrogen already present in reactive forms. Phosphorus plays a unique and critical role in biochemistry. It's part of the backbone of DNA and RNA, linking the sugar molecules together into the long chains that store genetic information. It's also central to ATP, the molecule that stores and transfers energy in cells. Phosphate groups can be added to and removed from molecules to regulate their activity, serving as switches that turn cellular processes on and off. There is no obvious substitute for phosphorus in these roles. Unlike carbon, nitrogen, and oxygen, which are abundant in the universe, phosphorus is relatively rare, created only in certain types of stellar processes. A planet poor in phosphorus might struggle to develop complex life, at least of the kind we would recognize. Sulfur contributes to protein structure through disulfide bonds, connections between sulfur atoms in different parts of a protein that help the protein fold into its proper 3-dimensional shape. Some organisms use sulfur compounds in their metabolism instead of or in addition to oxygen. Near hydrothermal vents on Earth's ocean floor, bacteria oxidize hydrogen sulfide, the compound that smells like rotten eggs, to generate energy. Entire ecosystems build on these chemosynthetic bacteria, demonstrating that sunlight and photosynthesis are not necessary for life. An alien world with extensive volcanic or hydrothermal activity could support life based on sulfur chemistry, even in complete darkness. Trace elements, though needed in tiny amounts, are essential for many biological processes. Iron is central to hemoglobin, the protein that carries oxygen in blood, and to many enzymes involved in energy metabolism. Magnesium sits at the center of chlorophyll molecules, enabling photosynthesis. Zinc, copper, manganese, and other metals serve as cofactors for enzymes, helping catalyze reactions that would otherwise proceed too slowly to sustain life. An alien biochemistry would likely require its own set of trace elements, perhaps using metals common on its world but rare on Earth, or finding entirely different solutions to catalysis and molecular structure. Water serves as the solvent for biochemistry on Earth, the medium in which all cellular chemistry occurs. Water has remarkable properties that make it ideal for life. It remains liquid across a wide temperature range, from 0 to 100 degrees Celsius at Earth's atmospheric pressure. It has a high heat capacity, meaning it resists temperature changes, which helps organisms maintain stable internal temperatures. Water molecules are polar, with a slight positive charge on one end and a slight negative charge on the other, allowing water to dissolve ionic compounds and interact with many different types of molecules. The hydrogen bonds between water molecules create surface tension, capillary action, and the unusual property that ice floats on liquid water, a characteristic that has profound implications for life in oceans and lakes. But is water necessary for life, or might other liquids serve as solvents for alternative biochemistries? Ammonia has been proposed as a possible alternative. Ammonia remains liquid at much colder temperatures than water. It freezes at -78 degrees Celsius and boils at -33 degrees Celsius at Earth's atmospheric pressure. A very cold planet, too cold for liquid water, might have lakes or oceans of liquid ammonia. Ammonia shares some of water's properties. It's polar, can form hydrogen bonds, and dissolves many substances. However, ammonia is a less effective solvent than water for many compounds, and the biochemistry that could operate in liquid ammonia would necessarily be very different from Earth's water-based life. Methane and ethane, though non-polar and very different from water, exist as liquids on Titan, Saturn's largest moon. Titan has lakes and rivers of liquid hydrocarbons on its surface, creating a hydrological cycle remarkably similar to Earth's water cycle, but operating at temperatures around -180 degrees Celsius. Could life exist in these hydrocarbon lakes? The chemistry would be completely unlike anything on Earth. Reactions that occur readily in water might not occur at all in methane, while entirely different reactions become possible. Cell membranes would need to be built from different molecules. The lipid membranes used by Earth's cells wouldn't function in liquid methane. Energy metabolism would follow different pathways. But some scientists argue that the sheer strangeness of Titan's environment doesn't preclude life, only life that operates on unfamiliar principles. Supercritical fluids represent another possibility. Under high pressure and high temperature, substances enter a supercritical state where the distinction between liquid and gas breaks down. Supercritical carbon dioxide, for instance, behaves as both liquid and gas simultaneously, with properties of each. Deep beneath the surfaces of certain planets, conditions might create supercritical water or other supercritical fluids that could potentially serve as solvents for exotic biochemistries operating under extreme conditions. Energy sources drive all biochemistry. On Earth, sunlight powers most ecosystems through photosynthesis. Plants and photosynthetic bacteria capture light energy and use it to build organic molecules from carbon dioxide and water. These organic molecules then flow through food chains, ultimately providing energy for all other organisms. But many alternative energy sources exist. Chemical energy from redox reactions, where electrons transfer from one molecule to another, can sustain life in complete darkness. Radioactive decay in a planet's interior could provide steady energy through the heat it generates, potentially supporting life in subsurface environments for billions of years, even if the star above has long since died. The origin of life, the transition from complex chemistry to living organisms requires conditions where organic molecules can form, concentrate, and begin the process of self-replication and evolution. On Earth, this might have occurred in tidal pools, in hydrothermal vents, in ice, or even in the atmosphere. The exact location and mechanism remain uncertain, but the chemistry required involves forming increasingly complex molecules from simpler precursors, eventually creating molecules capable of catalyzing reactions, including their own replication. This requires an energy source to drive uphill reactions that create complexity from simplicity, fighting against entropy. It requires some form of containment, membranes or surfaces, to concentrate molecules and create distinct chemical environments. And it requires time for random chemical processes to explore countless possibilities until self-replicating systems emerge. The universality of certain chemical principles suggests that life elsewhere, no matter how alien, would still obey the same rules of chemistry and thermodynamics that govern Earth's life. All life must extract energy from its environment and use that energy to create and maintain complex organization. All life must reproduce, passing information to offspring. All life must evolve through variation and selection. These requirements constrain the chemistry of life, regardless of what specific molecules are involved. Carbon is not the only possible basis for complex chemistry, water is not the only possible solvent, and oxygen is not the only possible energy source, but any living system must solve the same fundamental chemical problems: how to capture and store energy, how to build complex molecules, how to replicate information, and how to maintain organization in a universe that constantly tends toward disorder. The chemistry required for life beyond Earth encompasses the familiar carbon, water, proteins, and DNA, and the exotic silicon biochemistry in hydrocarbon seas, life in supercritical fluids, using metals we've never heard of, organisms metabolizing on reactions we've never imagined. The universe provides the raw materials everywhere: hydrogen from the Big Bang, heavier elements forged in stars and scattered through supernova explosions. Every planet, moon, and asteroid contains chemistry, happening constantly through radiation, temperature gradients, and the simple mixing of different compounds. Whether that chemistry crosses the threshold into life depends on having the right combination of elements, solvents, energy sources, and time, ingredients that might exist on countless worlds throughout the cosmos, waiting for chemistry to become biology in endless variations on the theme of life.